Welcome to this problem-solving session. Today, we'll be exploring a popular problem from LeetCode, problem number 179, largest number. In this challenge, we'll learn how to arrange numbers in a way that forms the largest numerical value. Let's dive in and uncover the most efficient strategies to solve it. The problem requires us to take a list of non-negative integers and arrange them in such a way that they form the largest possible number when concatenated. The result should then be returned as a string, since the number can be extremely large. For example, if the input is 10, 2, we can concatenate the numbers in different orders to form 102 or 210. To determine the largest number, we arrange 2 before 10, which gives us the result 210. This is because the concatenation 2 plus 10 is greater than 10 plus 2. Now consider another example where the input is 3, 30, 34, 5, 9. Here, we need to evaluate multiple comparisons to determine the optimal order. For instance, 9 should come first because 9 plus 5 is greater than 5 plus 9. Similarly, 34 should come before 30, as 34 plus 30 produces a larger result than 30 plus 34. By applying this logic to all elements, we arrange the numbers as 9, 5, 34, 3, 30, which gives the largest concatenated number 9534330. In another case, with nums equals 1, 10, 100, we see that 1 should come before 10 because the concatenation 1 plus 10 is larger than 10 plus 1. Similarly, 10 comes before 100 since 10 plus 100 is greater than 100 plus 10. Following these comparisons step by step, the numbers are arranged as 1, 10, 100, resulting in the string 110100. The constraints of the problem specify that the input array can have up to 100 integers, with values ranging from 0 to 1 billion. It's important to handle edge cases, such as arrays with a single number like 0, or cases where all numbers are zeros, such as 0, 0, 0, which should return 0. Another edge case involves numbers with shared prefixes, like 121, 12, which require careful comparison to determine the correct order. The crucial insight for solving this problem lies in creating a custom sorting rule. Instead of comparing numbers directly, we compare their concatenations in both possible orders. For two numbers x and y, we evaluate x plus y and y plus x to see which combination produces the larger result. By sorting the array using this rule, we can ensure the numbers are arranged to form the largest possible concatenated value. This custom sorting approach is key to solving the problem efficiently and correctly for all inputs. To solve the problem of forming the largest number from an array of integers, the simplest idea might be to generate all possible arrangements of the numbers. This is the brute force approach, where we generate every permutation of the input, convert each permutation into a concatenated string, and then compare to find the largest result. While this method guarantees correctness, it's computationally expensive due to its factorial time complexity. Even for moderately large input sizes, the number of permutations grows exponentially, making this approach impractical and infeasible in real-world scenarios. The key takeaway here is that while brute force works in theory, it lacks scalability and efficiency, which are crucial for solving problems with large inputs. Now, an optimized and more practical approach is based on custom sorting with a greedy strategy. Instead of generating all permutations, we focus on determining the optimal order of the numbers using a custom comparison rule. The insight here is that, for two numbers, the preferred order can be determined by comparing their concatenated forms. For example, if you have two numbers, say 3 and 30, you compare 330 and 303. Since 330 is larger, 3 should precede 30 in the final result. Using this rule, we can sort the numbers efficiently. The algorithm involves converting the numbers to strings, defining a custom comparator for the sorting order, sorting the array based on this comparator, and then concatenating the sorted numbers. We also account for special cases, such as when the array consists entirely of zeros. This method is efficient, with a time complexity of O(n log n) due to sorting, and avoids the inefficiency of generating permutations. By leveraging this greedy strategy, we can solve the problem in a scalable and elegant way. An alternative method to solve this problem involves a digit-based sorting technique similar to radix sort. Here, we pad all the numbers to the same length by cyclically repeating their digits and then sort them lexicographically. While this approach can theoretically work, it introduces unnecessary complexity. Handling the padding and cyclic repetitions makes the implementation cumbersome and harder to debug, which detracts from its practicality. Considering all options, the custom sorting approach emerges as the most balanced strategy. It strikes the right balance between correctness, efficiency, and simplicity. Unlike brute force, it avoids factorial complexity, and unlike radix-like sorting, it keeps the implementation straightforward. While it requires careful attention to the comparator function, it is efficient with O, n log n, complexity, handles edge cases cleanly, and leverages built-in sorting functions for reliability. Overall, the custom sorting approach is the most practical and scalable solution to this problem, ensuring clarity and correctness. In this problem, the goal is to form the largest number possible by rearranging a given list of non-negative integers. Think of it as taking numbers like 3, 30, 34, 5, and 9, and arranging them to create the largest concatenated number, in this case, 9534330. The key insight is that the order in which you concatenate these numbers significantly impacts the result. For instance, 9 followed by 34 forms 934, which is clearly larger than 34 followed by 9, which forms 349. This means we need to carefully determine the sequence of numbers to maximize the overall value. To do this, we create a custom sorting rule that evaluates pairs of numbers based on their concatenated values. By comparing whether x plus y is greater than, less than, or equal to y plus x, we can decide the correct order for each pair of numbers. If x plus y is greater than y plus x, then x should come before y. If it's less, then y should come first. And if they're equal, their order doesn't matter. Once we define this rule, we can sort the list accordingly. First, we convert all integers to strings, as concatenation operates on strings, not numbers. Then, we use the custom comparator to sort the list such that the largest concatenated values come first. This sorting process has a time complexity of O, n asterisk log, n, where n is the number of integers. After sorting, we simply join the sorted strings into one result. However, there are edge cases to handle. For example, if the list contains only zeros, like 0, 0, the result should be 0 instead of 2000. By addressing these cases, we ensure the algorithm is robust and produces the correct result in all scenarios. Standard numerical sorting would fail in a problem like this because it doesn't account for the concatenated value of numbers. For example, numerically, 30 is less than 3, but when concatenated, 30 plus 3 gives 303, which is smaller than 3 plus 30, which is 330. Therefore, we need the custom sorting rule to ensure the numbers are ordered based on their concatenated values. This approach also handles edge cases effectively. If the input is all zeros, such as 0, 0, the output is simply 0. For a single-digit input like 1, the result is straightforward, just 1. And for mixed-length integers, such as 3, 30, 34, the algorithm ensures the correct order by comparing the concatenated results for each pair. By converting integers to strings and using a custom comparator, we can reliably determine the correct order for any input. Now let's look at the Python implementation. First, we convert the integers to strings, as we need to compare concatenated values. Then, we define a custom comparator function. This function takes two strings, x and y, and compares their concatenated forms, x plus y and y plus x. If x plus y is greater, it returns -1, meaning x should come before y. If x plus y is smaller, it returns 1, meaning y should come before x. If they're equal, it returns 0. Using this comparator, we sort the list of strings. After sorting, we join the strings into a single result. There's one final check: if the first character of the result is 0, it means the input was all zeros, so we return 0 instead of 000. This implementation is both efficient and handles edge cases gracefully. For example, with the input 3, 30, 34, 5, 9, the sorted order is 9, 5, 34, 3, 30, which concatenates to form 953, 4330. Analyzing the complexity of this algorithm, the sorting step is the most expensive part. Sorting the list of n integers has a time complexity of O, n asterisk log, n. Within the custom comparator, comparing two strings involves concatenation, which has an average case complexity of O(1). Therefore, the overall time complexity of the algorithm is O(n * log n). On the space complexity side, we need O(n) space to store the string representations of the integers. Additionally, the sorting algorithm may require extra space depending on the implementation, but the overall space complexity remains O(n). This makes the algorithm efficient in practice, as it avoids the need to generate all possible permutations, which would be computationally prohibitive with a complexity of O(n). Instead, we achieve the same result using sorting, which is significantly faster for large inputs. This approach is both optimal and efficient. By comparing concatenated values, we ensure that each number is placed in the position that maximizes the overall result, adhering to a greedy strategy. It avoids the inefficiency of generating and evaluating all possible permutations, reducing the problem to sorting with a custom comparator. Furthermore, the algorithm is robust, handling edge cases like all zeros, single-digit inputs, and mixed-length integers seamlessly. By leveraging sorting and custom comparisons, we achieve a practical solution to the problem with optimal time and space complexity. This makes the algorithm not only elegant but also highly suitable for real-world applications where input sizes can be large. It's a great example of how a simple yet clever insight, comparing concatenated values, can lead to an efficient solution for what initially seems like a complex problem. The given code solves the problem of forming the largest number by arranging a list of non-negative integers. Here's a detailed explanation. Step-by-step explanation. 1. Convert integers to strings. The input list nums contains integers, but concatenation and comparison require strings. We convert all integers to strings using map, str, nums, ensuring each number is treated as a string during comparisons. 2. Define a custom comparator. The function compare is defined to determine the order of two numbers, x and y, based on their concatenated values. Specifically, if x plus y, e.g., 34 plus 5 equals 345, is greater than y plus x, 5 plus 34 equals 534, x should come before y. Thus, the function returns -1. If x plus y is less than y plus x, y should come first, and the function returns 1. If both concatenated results are equal, the function returns 0. 3. Sort the list using the comparator. The nums.sort function sorts the string list based on the custom comparator. The cmp_to_key function from functools is used to adapt the comparison function to work with Python's sorting mechanism. For handle edge case, if the largest number in the sorted list is 0, the entire result would be 0. This is checked explicitly, and 0 is returned in such cases to avoid results like 0, 0, 0. 5. Join sorted numbers. Finally, the sorted list of strings is concatenated into a single string using .join, nums, forming the largest possible number. Example. For the input, 3, 30, 34, 5, 9. After conversion, the list becomes 3, 30, 34, 5, 9. The custom comparator sorts the list into 9, 5, 34, 3, 30. Joining the elements results in 9534330, which is the largest number possible. Complexity. Time complexity. Sorting takes O(n log n, where n is the number of elements in the list. Space complexity, O(n), for storing the string representations. This implementation is concise, efficient, and handles all edge cases, such as inputs with zeros. Here, we begin implementing the solution in Java. First, we import the necessary packages and define the solution class along with the largest number method. The input to this method is an integer array called nums. To start, we convert this integer array into a string array. This allows us to manipulate the individual numbers as strings during the sorting process. We use a simple loop to iterate through the input array, and for each integer, we convert it into a string using string.valueOf, storing the result in the number strings array. Next, we define a custom comparator for sorting the strings. The idea here is to decide the order of two numbers based on their concatenated forms. Specifically, for any two strings a and b, we compare the concatenated results of a plus b versus b plus a. If the concatenation b plus a produces a larger value, it means b should come before a. This ensures the strings are sorted in descending order based on the concatenated results. After sorting, we handle a special edge case. If the largest element in the sorted array is 0, the entire result should simply be 0, since numbers like 0, 0 would otherwise produce an invalid result. Finally, to construct the largest number, we use a string builder to concatenate all the strings in the sorted array, appending them one by one. With the sorted strings now concatenated in the correct order, we simply return the final result. The largest number method returns the string representation of the largest number constructed by concatenating the elements of the input array. This completes the implementation. By sorting based on the custom comparator and handling edge cases like all zeros, we ensure correctness while keeping the code efficient and concise. To solve this problem, we start with the input list 10, 2. The first step is to convert each integer in the list into a string. This allows us to perform string concatenation, which is key to determining the correct order. After this step, the list becomes 10, 2. Next, we define a custom comparator function called compare x, y. This function will help us decide the order by comparing two strings based on their concatenated results. If x plus y is greater than y plus x, it means that placing x before y creates a larger number, so the function returns -1. Conversely, if x plus y is less than y plus x, it means that y should come first, so the function returns 1. If the two concatenations are equal, the function returns 0, indicating no preference. Using this comparator, we sort the list. For example, when comparing 10 and 2, we calculate 10 plus 2 as 102 and 2 plus 10 is 210. Since 210 is greater, 2 should come before 10. After sorting, the list becomes 2, 10. Now that we have the sorted list, 2, 10, we check for an edge case. If the first element of the sorted list is 0, it means all the numbers are zeros, and the result should simply be 0. In this case, the first element is 2, which is not 0, so we move forward. The next step is to concatenate all the strings in the sorted list. Joining 2 and 10 gives us the string 210. This is the largest number that can be formed by concatenating the input integers. Let's move on to another example with a larger input, 3, 30, 34, 5, 9. First, we convert all the integers to strings, resulting in the list 3, 30, 34, 5, 9. With the input list 3, 30, 34, 5, 9, we now sort the strings using the comparator function. Starting with 30 and 3, we calculate 303 and 330. Since 330 is larger, 3 comes before 30. Next, we compare 34 foot and 30. Here, 3,430 is greater than 3,034, so 34 comes before 30. Moving on to 5 and 34, we find that 534 is greater than 345, so 5 comes before 34. Finally, comparing 9 and 5, we see that 95 is greater than 59, so 9 comes before 5. After all comparisons, the sorted list becomes 9, 5, 34, 3, 30. We then check for the edge case where the first element is 0, but here, the first element is 9, so we proceed. Concatenating all the strings in the sorted list gives us 953, 4330. This is the largest number we can form from the input. For the final example, the input is 0, 0. As before, we first convert all integers to strings, resulting in the list 0, 0. Sorting this list doesn't change the order since all elements are identical. The sorted list remains 0, 0. Now, we check the edge case where the first element is 0. In this scenario, the first element is indeed 0, which means the entire number formed by concatenating the elements will also be 0. Therefore, the final output for this input is simply 0. To analyze the time complexity of our solution, we break it into 3 major steps: converting integers to strings, sorting the strings with a custom comparator, and concatenating the strings into the final result. First, the conversion step involves transforming all integers in the input list to strings. This is done using the map function, which processes each of the n elements in the list, resulting in a time complexity of O(n). Next, we have the sorting step. Sorting the strings requires O and log n comparisons, as expected in a typical sorting algorithm. However, each comparison is more expensive here due to the custom comparator, which involves concatenating two strings like x plus y and y plus x. Since the length of a string can be at most O, k, where k is the number of digits in the largest number, each comparison takes O, k, time. This makes the total sorting time complexity O, n log n asterisk k. Finally, in the concatenation step, we join the sorted strings into the final result. As we process n strings, each of average length k, this step takes O, n asterisk k, time. These three steps together define the time complexity of the solution. When we combine the time complexities from the three steps, the sorting step dominates the overall calculation, giving us a final time complexity of O, n log n asterisk k, where n is the number of elements and k is the maximum number of digits in the largest number. Now, turning to the space complexity, we need to consider both the auxiliary space used during computation and the space needed to store intermediate results. First, converting the integers to strings requires O, n asterisk k, space, as we need to store n strings, each of average length k. Then, the sorting algorithm, which is timsort in Python, requires an additional O, n, space for temporary storage during sorting. Finally, the concatenation step results in a single string that also requires O, n asterisk k, space to store the largest number. These components together contribute to the total space complexity. When we evaluate the total space complexity, the storage requirements for the input conversion and the final result dominate, resulting in O, n asterisk k, overall. To put this into perspective, let's compare this optimized solution with a brute force approach. In a naive method, we would generate all possible permutations of the input numbers, concatenate each permutation into a string, and then select the largest one. This would require O n permutations, with each permutation taking O, n asterisk k, time to concatenate and compare. This results in a time complexity of O, n asterisk k, which is computationally impractical for large inputs due to the factorial growth of n. By contrast, the optimized approach, which reduces the problem to sorting with a custom comparator, achieves a time complexity of O, n log n asterisk k. This is a dramatic improvement and makes the solution feasible even for larger inputs. Now, let's analyze the time complexity across different cases. In the best case, if the input numbers are already sorted in descending lexicographical order according to our custom comparator, the sorting step still takes O, n log n asterisk k, time, as the sorting algorithm needs to verify the order. In the average case, the complexity remains O, n log n asterisk k, as this step continues to dominate the overall computation. Similarly, the worst case also has a time complexity of O, n log n asterisk k, since the sorting algorithm handles the maximum number of comparisons in this scenario. To mathematically justify this, note that the dominant term arises from the sorting step. With n elements, there are O, n log n, comparisons, and each comparison takes O, k, time due to string concatenation. This holds true regardless of the input order, making the complexity consistent across all cases. This efficient sorting-based approach is what enables the solution to scale well compared to brute force methods. Let's start by addressing some common mistakes that developers encounter when solving the largest number problem. The first issue is using incorrect sorting logic. Many people mistakenly sort the numbers as integers, which leads to incorrect results. For instance, if you sort 9, 34 numerically, you get 34, 9. However, when forming the largest concatenated string, the correct order is 9, 34. The solution is to sort the numbers based on their string concatenations. Specifically, for two numbers x and y, you compare x plus y versus y plus x to decide the order. Another mistake is relying on inefficient brute force solutions. Generating all permutations of the numbers and checking each concatenated result has a factorial time complexity, which is impractical for large inputs. Instead, using a custom sorting strategy is far more efficient. Neglecting edge cases is another common pitfall. For example, if the input is 0, 0, 0, concatenating these should return 0 instead of 0, 0, 0. To handle this, check if the first character of the result string is 0 and return 0 in such cases. Finally, some implementations fail when the input contains non-numeric elements like strings or floats, leading to runtime errors. To prevent this, validate the input or cast all elements to strings before processing. Another common issue to be aware of is modifying the input list directly. Sorting the list in place can lead to unintended side effects, especially if the input is used elsewhere in your program. To avoid this, work on a copy of the input list or take a functional approach. Now, let's talk about some key insights for tackling this problem during interviews. At its core, this is a sorting problem where the main task is to compare concatenated strings, specifically x plus y versus y plus x, to determine the order. This insight simplifies the problem significantly and eliminates the need for brute force approaches. When discussing your solution, it's important to ask clarifying questions, such as the maximum length of the input list and the range of numbers allowed. Edge cases like 0 or 0, 0 are also worth confirming. Efficiency is another critical factor. In an interview, emphasize that your approach has a time complexity of n*log n, which is optimal for a sorting-based solution. Finally, always test your solution with edge cases, such as single-element inputs, lists with all zeros, and inputs of varying sizes, to demonstrate its robustness. Let's explore related problems that share similar concepts. First, there's LeetCode 179, which is the exact largest number problem we're discussing. Then there's LeetCode 937, reorder data in log files, which also involves sorting with custom rules. Another is LeetCode 56, merge intervals, where careful comparison logic is required while sorting and merging intervals. Lastly, LeetCode 49, group anagrams, focuses on sorting strings to group them, further highlighting the importance of sorting strategies. When it comes to alternative approaches, the most common is using a custom comparator with sorting. Here, you sort the numbers as strings based on concatenated results, comparing x plus y against y plus x. This approach is efficient, with a complexity of n*log n, and is relatively straightforward once you understand the custom sorting logic. Another option is a greedy approach, where you iteratively build the largest number by selecting the optimal next number based on string concatenation. While this approach can be effective, it's often harder to implement and debug compared to the sorting-based solution. Finally, let's consider the brute force approach, which involves generating all permutations of the input list, concatenating each permutation, and selecting the largest result. Although this method provides a direct way to solve the problem, it's extremely inefficient, with a factorial time complexity of n. This makes it impractical for larger inputs and unsuitable for real-world use. However, it can still be useful in understanding the problem space, especially for simpler cases or when you're trying to validate the correctness of other solutions. While brute force is not recommended for optimal solutions, it's a helpful stepping stone in grasping the core logic of the problem. Great job working through this problem. To summarize, we tackled the challenge of arranging numbers to form the largest value using custom sorting. We reviewed edge cases and emphasized the importance of efficient algorithms. Thanks for tuning in. Be sure to like and subscribe for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!